Hello everyone. So in this video I'm going to be talking to you about testing the significance of the relationship between x and y. So here we have our simple linear regression model. Let's not forget that it is made up of two components. We've got the mean level component, which is explained by x over here. It is generated by x. And then we've got the error term component, which is this random part of y that cannot be explained by x. If I use here my sample of 10 randomly selected restaurants over here, I've got my 10 x and y observations, and so as a result of this, I'm able to get some point estimates through method of least squares for my slope. So this is my B1 value, and I get a point estimate for my y-intercept. So here is my B0 value. And of course, this depends on the sample observations that I was using, right? So if I'm going to be testing the relationship between x and y, this can be done through hypothesis testing. In fact, in this in this video, we're going to look at 3 hypothesis tests that do just that. And it can also be done by setting up any type of interval around a point estimate. So we're going to be looking at that as well. But before we do any type of hypothesis testing or construct any type of interval around a point estimate, we need to work with some assumptions. So the first 2 hypothesis tests that we'll look at are based on the 4 model assumptions that we saw in a previous video for the error terms. And it is summarized very briefly here by this statement right here, and that is that at any given value of x, there is a population of observed yi's, and hence a population of error terms, e of I. And these error terms follow a normal distribution. They are independently distributed and identical with a mean value 0 and a standard deviation sigma. If that is the case, then of course it is possible to generate samples of size n that will give me different slopes, right? So the sample of size 10 that I happen to have selected for my restaurants gave me a slope here of 15.596. But if I had chosen a different sample for the same x values, then I would have generated possibly a different B1 value. So in other words, there is a whole population of different B1 values. There is a whole population of different, of potential different estimates for the slope B1. Okay, let's not forget here what the equation is, using the method of least squares. The equation to determine the estimated slope is the sum of squares of the x and y divided by the sum of squares of the x's. And so we say that the slopes are normally and identically and independently distributed with mean value beta 1, that is the population value, and the standard deviation is a sigma of B1. Okay, so sigma here comes from my standard deviation for the error terms. When I have all the error terms available, I am able to get my standard deviation for population. So here we have the equation for standard deviation of the slope for the point estimate slopes, and that is sigma divided by the square root of the sum of squares of the x's. But that, of course, is when my population standard deviation for the error terms, for the residuals, is known. When I don't know my population standard deviation for the residuals, then I must use a sample standard deviation. And that sample standard deviation we've seen before is called the standard error. The standard error is in fact the square root of the mean squared errors. Okay. And so we see that the standard error for my estimated slope, so my standard error for B of 1 is in fact, so my sample standard deviation, or in other words, my standard error of the residuals, divided by the square root of the sum of squares of the x's. Okay, and very quickly here, I remind you here what the sum of squares of the x's is equal to. Now, I want to show you what is really going on through a picture right here. So let me just zoom in, and here we are. So this is really what is going on. We've got here our true regression line. That is the dark green line that we see right here. Of course, we don't know what that true regression line is. We don't know where it really is when we take samples of size n. So here we've got a first sample of size n. That's the light green line, and it's giving me a slope, an estimated slope B1 that yields such a line. Okay, so this is one of the many B1s that is potentially estimated over here. In another scenario here, see the orange line. This is another the result of another sample of size n, n always being the same, of course. And here we get another slope B1. We're getting another slope B1, and so we see how this line varies about the true regression line. And finally, another sample. We've got a third sample of size n. So here, what's happening is each time I take a different sample, well, I'm getting different y values, right? For each x value, I'm getting different observed y values, and hence I'm getting different error term values, right? But of course, these error terms in the big picture must follow the four model assumptions that were discussed before. So this is one scenario. In this case here, what is happening is we're getting a large spread of the different sample lines, and that is because over here the standard error of the residuals is probably very large, hence giving this wide dispersion about the true regression line. On the other extreme, when the standard error of the residuals is small, right? Well, this means that your point estimates are very close to the true population values, and so we are getting very little dispersion. Hence, the standard error of the residuals is small. So we see how the dispersion about the true regression line is decreased significantly. Okay, so you understand the importance of the magnitude of your standard error of residuals plays a key role in determining how large or how small your standard error for your slope will be, right? Okay. So let's look at these hypothesis tests, and we'll also look at an interval. Okay. So the first hypothesis test we look at is testing the significance of the slope. And this is done by saying in the first place that the mean value of the y does not change as a result of the unit increase in x. Hence, beta 1 here equals 0. Remember that in hypothesis testing, we always use population parameters in our hypothesis statements, right? So here we're saying that for the null hypothesis, and the alternative, we're saying that there is a positive or negative change in mean value of y as a result of a unit increase in x. Okay, positive or negative, we don't know here, and hence here we say that beta 1 does not equal 0. Okay, so this is a two-sided test. And of course, we're going to test out this hypothesis, the null hypothesis here. We're going to test it out at a given level of significance. So say here we let alpha equal 0.05. So at 0.05, we will conduct the test. And okay, here we are. So we're going to need a test statistic to compare to a critical statistic, to a critical value, right? So the test statistic will always, of course, measure how far or how close our sample value is relative to the population value that is claimed in the null hypothesis. And of course, this test statistic is always standardized so that it is divided by in this case, the sample standard error, right, for the slope, for the estimated slope. So this is the formula that we use to obtain our test statistic. So I'm going to have to figure out what my B1 is, which I can get by applying the method of least squares to my sample of observations. And my beta 1 here will be 0 because that is what is being claimed in the null hypothesis. And I will divide by this standard error for B1. And I will compare it to a critical value, T of alpha over 2, and for known degrees of freedom. So let's not forget that there is a different T distribution for each degree of freedom, okay? And here my level of significance must be divided by 2. My alpha must be divided by 2 because I am using a two-sided test over here. The two-sided test is determined in my H of A, right? Okay, degrees of freedom will always be, in this case for simple linear regression, it will be n minus 2, okay? And so I will get this information to conduct the test. Either I can manually compute through method of least squares what my B1 is, and I can also manually compute my standard error for my estimated slope. But there is also a faster, easier way to do this, and that is by using some statistical package. So Excel being the most widely used package out there, but of course there are plenty of other statistical packages, but I'm going to use Excel here to illustrate my examples. So in Excel, this is what we get when we apply the regression analysis tool to our sample observations. Okay, so here we are getting our coefficient, our correlation coefficient, that's in the first line right here. That's your multiple R. Then the R square, well, that is your coefficient of determination. Okay, then our standard error, let's not forget our standard error, that's a key statistic that we need. That is in fact your square root of MSE. That is the square root of MSE. That is your standard error of the residuals, okay? And then we have here the breakdown of the different sources of variation in Y. So we've got our regression source of variation, which is also known as the SSR. That's the explained variation. Okay, so here it is right here. Then underneath that, we've got the unexplained variation. So that is everything that is not explained by X is explained by this random component of y. So this is your SSE. And then finally, when we add these two sources of variation, we should get our total variation. Total variation is SST. Okay. And here in this column right here, we get the mean squared error terms. So the mean squared explained variation is in fact taking the SSR and dividing it by its degrees of freedom. So here, because I am using one predictor to predict y, that is my 1x in simple linear regression, then I've got here 1 degree of freedom. We'll see in later video how in multiple regression, this degrees of freedom will no longer stay at 1, right? It will reflect the number of predictors that we are using in our regression model to explain y. And then here my mean squared error term for the unexplained variation is looking at the SSE and dividing it by its degrees of freedom here, this being n minus 2. So if my sample has 10 observations, I must subtract 2 from that to get me 8. 2 because over here, once again, I need to estimate 2 parameters. My y-intercept parameter needs to be estimated, and my slope my slope parameter needs to be estimated as well, right? So that is why I am subtracting by 2. Yes, that's right. And then finally, this is my sum of squares of the total variation. Notice that it has 9 degrees of freedom. So in fact, it is the sum of these 2 degrees of freedom. The 8 plus the 1 gives me 9. Don't forget, though, that I do have 10 observations in my sample. So total degrees of freedom, 9, is not the same as total number of observations I have in my sample. Just keep that in mind. Okay, so in my further in my output here, I have this other part, and that is the estimated regression line, or the fitted regression line coefficients, and there's corresponding standard errors. So that is very interesting here. So here I have, in fact, my standard error for my slope, B1. That is this value right here. And this is as a result of, let me just go back to the formula for the standard error of the slope in my sample. The standard error of the slope, S of B1, is equal to my standard error of residuals divided by the square root of the sum of squares of the x's. So in fact, the statistical package takes care of it for you. You don't actually need to compute anything here. It will do all the computations, and it will give you here the actual product of the standard error. Okay, so now I can get my t-test value by plugging in the right values in my formula. And so I get here a value of 11.0548. Notice that my statistical package actually gives me that value as well in the next column here, t-stat. So that's great. So you don't even need to compute the t-stat. If you know how to read the output, then you can actually extract all the needed information to answer your questions. So this t-stat value must be compared to a critical t-value. Now I need to go look at my t-table and determine what is that critical value. So that here, let me just go back here and see, well, if I'm doing my testing at a level of significance of 0.05, this means that my t will have an alpha value of 0.025, and it will have here degrees of freedom. 10 minus 2 gives me 8. So I get here my 2.306. Let's just go quickly into the t-table and see how we get this critical value. So once again, I'm looking at a t-point for 0.025, an area here of 0.025, and I'm looking at 8 degrees of freedom, so it gives me this value right here. Okay, so I have my critical value, I have my test value, and the decision rule is if I'm using the critical value approach, I reject my null hypothesis is if my test statistic is greater than my critical value. And so indeed here I see that it is. Okay, if I were to use the p-value approach, because let's not forget this is another way of um, making a decision here is by using the p-value approach. Well, in this case, what we say is we look to see what is the probability of finding a t value that is greater than the t-test value for a given degrees of freedom when, of course, we are assuming that the null hypothesis is true. What is that likelihood? And so that is what the p-value gives us. Now, since this is a two-tailed test, then let's not forget that the p-value here is as a result of multiplying this probability here by 2, simply because the test, the p-value is separated here in the two tails, the right tail and the left tail. So I must multiply this probability here by 2. And, well, actually the Excel package does it for you, so you don't even need to compute it. But this is what I'm getting over here. When Excel does it for me, it tells me that the p-value is extremely small. The likelihood of finding a t value that is greater than 11.0548 for 8 degrees of freedom, when we assume that the null hypothesis is true, is very unlikely. That is what this p-value is telling me. Okay? And so the rule is if your p-value is less than the level of significance that is specified at the beginning, then you can reject the null hypothesis, and such is the case over here. Just a reminder that when you use either critical value rule or p-value rule to make a decision in your hypothesis testing, you must always get the same conclusion. Okay? Now here I just added a few little extra notes, and that is that sometimes this hypothesis test can be one-sided. It doesn't always have to be two-sided. So there are instances when we believe that in fact the slope is negative. And so the testing will be different, right? So the way we compare our test statistic to our critical value is different here. So we compare it such that the test statistic here, which will be negative, it should be negative, right? Because here we are assuming that our sample slope is negative, right? We're basing ourselves on a negative sample slope, B1. And so that is how we come to state in the alternative hypothesis that the beta 1 is in fact less than 0. And so here the decision rule is that you reject the null hypothesis if your t-test is less than your critical value, which will of course be negative here because the testing is happening on the left side of the t-distribution. Hence you must put a negative sign in front of your critical point right here. Okay, so you can review this at your own pace. Okay, so yes. Okay, so yes, sorry. So this was in the scenario when we are still okay. So this was the scenario here. It is this one right here that I just explained. It would be applied with this type of scenario when we are using a one-sided test. Yes, when we are using a one-sided test over here. Okay. So that is one hypothesis test. So basically, we are evaluating if the population slope is equal to 0 or not. Okay. Then we look at another option over here, and that is building a confidence interval for beta 1, the population slope. So the population slope here, of course, will be based on the point estimate slope that we're getting from our sample observations. So here we get a sample slope B1, and around it we're going to build some sort of interval. Call this, if you want, a margin of error. The margin of error is made up of a critical point, which is based on your level of confidence, um, and it is also based on your standard error for the estimated slope. Okay, so in the case of a 95% confidence interval for the population slope, well, what I want to do is use my point estimate um, that I got by application of method of least squares, plus or minus this critical T point, which is determined based on the level of confidence. So if my confidence interval is 95%, this means that I have a 5% area of rejection, if you want. So this is this area of 0.05 is split in two equal parts, such that now I have an interval that contains 95% of my point estimates for beta 1. Okay, and I multiply that by the standard error for the standard error for B1, which I get from my sample. And so here, if you can follow with the values that I am plugging into my formulas right here, I get this confidence interval. This is a 95% confidence interval for beta 1. So it ranges here between 12.3424 and 18.8488. Okay. So what it means is that each time the population size increases by 1 unit, which let's not forget is 1,000 residents, then the mean yearly revenue will increase by at least $12,324 and some odd, and by at most $18,000 and 848 sorry, $18,848 and some odd. Yes. Okay. Now, one key thing to note here is that my confidence interval here does not contain the value 0. Notice how my confidence interval does not actually contain the value 0 in between here, in between these two values, which is a good sign. It means that I can reject my null hypothesis. So if I go back to my hypothesis statement over here, the hypothesis statement was right here. We said that the null hypothesis says the slope, the population slope, equals 0. But notice that when I build a 95% confidence interval around my point estimate that I'm getting from my sample observations, well, I see that, in fact, there is no 0 contained in that interval, right? So right away, I know with 95% confidence that my my population slope will not equal 0. In other words, I can I have a level of significance of 5% of committing a type 1 error. There is a 5% chance that I am committing a type 1 error over here. So that is how we can use confidence intervals to also address the significance of the relationship between X and Y, right? So here I do know with 95% confidence that the beta 1 does not equal 0 here because I have this 95% confidence interval right here. Okay, and so this can also be done for building a confidence interval for beta naught, say. So what I would do is use my point estimate for beta naught being B naught, plus or minus here the critical point t of alpha over 2 with degrees of freedom n minus 2 times the standard error for B naught. Okay, so this is something that is mentioned in the textbook here where you can look at the formula for that. But most often we are really interested in testing the slope because the slope is what really ties x and y together, right? Okay. So now let's move on to the second hypothesis test. Okay, the F test for significance of the linear regression model. So this test here is more general if you want. We're not just looking specifically at beta 1, whether it is equal to 0 or not, but rather a general, we're trying to make a general assessment over here to see if there is some significance in the linear regression model. And so this test really becomes useful when we start to look at multiple regression models. Okay, but for the moment here, this F test is pretty much doing the same thing that the first test did for testing the slope for beta 1. Okay, so as you can see, even here, we have the null and alternative hypotheses are stated in the same way as before. However, here, this will remain a one-tailed test. It will not be two-tailed. Okay, so in other words, we'll be comparing our test statistic F, which I'm going to explain to you in a little bit. We will be comparing it to a critical F value for alpha and not alpha over 2. It will be for alpha right here. So this is the test statistic that we get from our sample observations. We are comparing the explained variation divided by the number of parameters in our regression model. So in simple linear regression model, k here equals 1 because we've only got one predictor. Yes, we've got one predictor over here. That is what I meant to say before. It's not the number of parameters, but rather the number of predictors or independent variables to explain why. So yes, please correct that. So here I'm looking at the number of predictors. Here I've got one predictor, x. And so I take my SSR, let's not forget explained variation is in fact SSR, and I will divide it by 1 in this case, and all of this here will be divided by the unexplained variation, divided by here this little math equation here. So we've got n minus k minus 1. So n here being the sample size, I've got 10 observations in my sample. I've got one predictor, so that is 1. And here I've got minus 1. So hence this is really the unexplained variation that is divided by n minus 2 for simple linear regression. And so we see that the F test is based on this ratio right here, or on this proportion of explained variation, the mean explained variation relative to the mean unexplained variation. And we will compare it to a critical value, f of alpha, for two sets of degrees of freedom. The first degrees of freedom is coming from my numerator, and so that will be equal to k, so that's 1 in this case. And my second degrees of freedom, d of f2, is coming from my denominator, so it will be n minus k minus 1. Let's just quickly look at what the F distribution looks like. So here we are. This is the F distribution very quickly. And so there is a different F distribution for different degrees of freedom, of course, for different pairs of degrees of freedom. So it gets a little tricky. Very quickly here, this is one table of the F distribution. So you will have a different table for different alpha values. Here we are looking at a table for alpha equal to 0.10. And for alpha equal to 0.10, we've got here a different set of F distributions. These are all the F points. So when my D of F1 equals 1, which is what we're looking at over here, I'm looking at simple linear regression, so I only have one predictor, so my D of F1 equals 1. So I'm really focused on this first column right here. And then the df of 2 will depend here on my sample size, right? It will depend on my sample size. Sample size, of course, minus k minus 1, right? Okay, let's go back to the slide. Okay, here we are. Yes. So here we see how the F distribution is skewed to the right. It has a skewness to the right, and the testing is done on one side. It is a right-tailed test, a one-sided test, and the rule here, the decision rule, is we say that we reject the null hypothesis if the F test is greater than the critical F. Okay, and so that will always be the decision rule that we apply over here. There is no other way, there is no other direction in which the arrow points. It will always be this in this form right here. And so here, notice that we are using alpha as our rejection region over here. It is alpha and not alpha over 2. It is always alpha. And so if my F test value happens to be in the rejection region here of, say, alpha equal to 0.05, then I will reject my null hypothesis, which is saying that beta 1 population slope is equal to 0. I will reject it if my F test is in that region. Okay, that is using the critical value approach. So yes, here I get, when I go in my table, my F table, my critical value here happens to be for an F of 0.05, a DF of 1 equal to 1, and a DF of 2 equal to 8. So let's go look at that critical value. I'm just going to scroll down. Here I've just taken an excerpt of an F distribution for alpha equal to 0.05. And this is what I'm getting right here. So notice how I am crossing my degrees of freedom for numerator with my degrees of freedom for denominator, 1 and 8, and I get here a critical value of 5.32. Now let's go back up. And so we see that, so now the F test value is obtained by applying this formula right here, which we can get from our regression output in Excel or any other statistical package, which is also equal to this. Or if you want, you can just go straight to your Excel output and get these values, right? You can obtain the F test value directly. So I'm going to bring you to that right now. Yes, here we are. So this is the Excel output that we have right here. And if we look carefully in the ANOVA section, this is otherwise known as the analysis of variance section of the regression analysis, right? So this section, ANOVA, contains over here, yes, we have the sum of squares for explained, unexplained, total variation, but we also have the F-test value. So the F-test value here is done by applying the formula we saw, and so we get a value of 122.2096. You can compare by computing manually if you want to see if you get the actual same F-test value. That is easily done by taking your sum of squares over here, dividing by 1, over this sum of squares, dividing by 8, and you should really get the same value right here. Further to that, the Excel output also provides you with the p-value for the F-test value that we get here. So the p-value, which is here called significance f, is very small, right? We see that it is pretty much 0. Okay, so let me just get back to where we were. So here we are. So the decision rule is this using the critical value approach. If I am to use the p-value approach, then, it's the same idea. Once again, if your p-value here, which we saw in our output, was 0, is less than the level of significance alpha, which we specified here to be 0.05, then we get here then we reject the null hypothesis. And here, quickly, I define the p-value. How do you compute the p-value? The p-value is based on the assumption that the null hypothesis is true, and so then we look for the probability that you find an f value greater than the test statistic value that you computed right here for degrees of freedom in the numerator equal to k, degrees of freedom in the denominator equal to n minus k minus 1. Okay. So in fact, let's just do a quick exercise over here. My test value of 122.2096. Well, if I were to find the corresponding p-value in the table, let's just go over here. So first of all, yes. So I'm going to look first in the table for alpha equal to 0.1. And I'm going to try to go find a combination of df1 equals 1 and df2 equals 8. And so here the f value that I find is 3.46. It is not remotely close to the 122 and some odd that I found for my test statistic f. This means that my p-value is clearly smaller than 0.1. So I must continue to move on to the next f table. The next f table I have is for alpha equals not alpha, sorry, but the right tail area is equal to 0.05. At at a right tail area of 0.05, I get here for degrees of freedom 1 equals 1 and degrees of freedom 2 equals 8. I get this 5.32, not remotely close to the 122 and some odd that I get from my test statistic. So I must continue to work with a smaller right tail area. So I continue here in my tables. Here I get another table. This table right here. Here I see that my p-value is I cannot get my p-value from this right tail area here because my test statistic f is not even close to 7.57. So let's see, I believe I have another f table here. I think that is the smallest right tail area that I have in my tables. Yeah, and in here I can see that for degrees of freedom 1 equal to 1 and degrees of freedom 2 equal to 8, I am getting here an f value of 11.26. It's not close to the test value f that I got of 122, but it's the best value I'll get. So how do I conclude that? Well, what I can say is, if I were to rely on the tables only, what I can say is that my p-value will be less than the smallest value I found in my tables. The value I found here, the right tail area that I found was 0.01, and that provided me with the highest f point that gets close to the test statistic f value. So pretty much here what I could say if I were using the tables and not using any statistical package, what I could say is that my p-value for this example is less than 0.01. It is less than 0.01. And if it is less than 0.01, then that means that it is less than the alpha the level of significance of 0.05. So if it is less than the level of significance, this means, once again, that I can reject my null hypothesis. Okay, so I've shown you two hypothesis tests and how to work with an interval, build a confidence interval, in fact, for um, uh, the population slope based on a point estimate that I get from a sample of observations. And of course, these were all based on the four model assumptions about the error terms. Now we look at another hypothesis test, and that one is not based on the four model assumptions, but rather based on the assumption that x and y follow a bivariate normal distribution. In other words, x and y are normally distributed. This is the assumption we are making. If they are both normally distributed, then we can say, then we can use this type of hypothesis test. And that is about the, the population correlation coefficient, rho. So we've seen the population correlation coefficient and its equivalent sample correlation coefficient, r, right? So the idea is that we will now assume that the correlation coefficient, which measures the linear relationship between x and y, is demonstrating no linear relationship here in the null hypothesis. This is what it is saying. Versus in the alternative, we are saying that there is some sort of positive or negative linear relationship between x and y. Okay? And in this case, it is here it is a two-tailed, it should be two-tailed test. Let me just correct this over here. Here we are. It is a two-tailed test. Here we will use the t-distribution to conduct this hypothesis test. So of course we start again by specifying the level of significance in which we will do the hypothesis test, and then we determine what our test statistic is. Here the test statistic is in fact relying on the sample correlation coefficient, which we get from our sample observations, of course, and that is r, okay? And so yeah, so here the test statistic is r times the square root of your sample size minus 2, and that is all divided by 1 minus your sample correlation coefficient squared, and all of that is square root. And we compare that to a critical t value. The critical t value here will be based on alpha over 2 because it is a two-tailed test, not one-tailed. It is two-tailed, and it depends on degrees of freedom here, n minus 2. So here we are. We have here the decision rule, which says that if your t-test statistic here is greater than your critical value, then you reject the null hypothesis. So in fact, if you are to actually use your R, your sample R value, you can go and get that in your output if you want. You can actually go get that in your output. Let me just go show you right here. So here we are. In our Excel output, we do have the sample correlation coefficient. It is this value right here, 0.9688. So the 0.9688 will be multiplied by the square root of n minus 2. N is 10, so minus 2 gives me 8. So if I multiply this times the square root of 8 in my numerator, and I divide it by the 1 minus r squared in the denominator, so again that is feasible, you can do that by using your sample output, well, in fact, you will get a t-test value that is exactly the same value. I don't know if you remember, it is the same t-test value that I got from testing the slope in my first hypothesis test. So here I get 11.0548. And let's go back to the first test which we did. Um, here we were looking at this over here, beta 1 equals 0 versus beta 1 not equal to 0. The t-test took on this form, and it gave me, based on my computer output over here, I got this t-test value of 11.0548. And so it gives me exactly the same value that I get for the t-test value that I'm using now to address the hypothesis test of whether or not the correlation coefficient is 0 or not. Okay, so let's go back. My critical t value here will be determined in exactly the same way as it was in the first test, and it will be exactly the same value because, again, I am looking for a t value of 0.025 and degrees of freedom 8 equal to 8. The decision rules are the same. Whether I use the critical value approach or the p-value approach, the decision rules are the same. Okay, and what is interesting here to note is oh yes, so this is an alternative way to test the relationship between x and y. Okay, you can use this information here to test your x and y relationship. Yeah, one point which I forgot to mention before about the f-test is the following. Yes, when you are doing simple in your when you are working with simple linear regression models, here, one thing that is always true is that the df of 1 will always be equal to 1. Okay, because I'm always working with one predictor. That is what a simple linear regression model is all about, is having one predictor for y. Okay, then the next thing to note here is that the f-test will be equal to the square of the t-test value. So interestingly enough here, if you remember the f-test value that I got in my second hypothesis test was 122.2096, right? And if you look at the previous test statistic that I got through the other hypothesis test, well, I got here a t-test value of 11.0548. Well, if you square this 11.0548, you should get 122.2096 approximately. You should get, so the two are related. So in fact, when you square your t-test value, you should get the f-test value. This is only true for simple linear regression. We'll see that in multiple regression, that is not the case anymore. Anyway, I thought I would just point that out for you guys. And yes, finally, to conclude this video here, I just want to show you how you can also get information using Minitab. You can do your regression analysis through Minitab. And so the information is simply organized in a different way, but you do get your ANOVA information right here, where you've got here your explained variation, you've got your unexplained variation and your total variation. Your degrees of freedom are highlighted over here. Then in your model summary, you will get your standard error for the residuals. That's your square root of MSE. And you will also get here your coefficient of determination. Note though, Minitab does not give you the correlation coefficient, but that's not complicated to determine. You just take the square root of your coefficient of determination to get your correlation coefficient. Okay, so that is R square. Then here in this section, you are getting your model summary. So you're getting your coefficients, right? Notice how they are the same. You get your standard errors corresponding to each coefficient over here, and your t-values, corresponding p-values as well. Okay, going back to the analysis of variance here, you will get your F test statistic. The 122.2096 is found right here, and its corresponding p-value is right here. Okay. What is nice about the Minitab output is that it also provides further information on confidence intervals and prediction intervals around your point estimate Y value. So that I will discuss in a next video. I hope that this video has been useful for you, and we'll meet in the next one.